Right, so this is probably going to be pretty short, well, maybe not that short, but almost short reading group presentation. So I've been looking into trajectory optimization methods for legged robot locomotion of leads, or basically for trajectory optimization for robots in general. And I came across a iterative LQR, which is basically an extension of the LQR algorithm for trajectory optimization. And so most of this reading group would first start with a primer on LQR and extend it to iterative LQR, which is basically LQR, but then performed iteratively. And then we'll look at a code example in Julia. And yeah, that'll be it basically. Oops. Yeah, so iterative LQR is essentially a trajectory optimization algorithm. And trajectory optimization is basically a means of coming up with dynamically feasible trajectories that obey certain constraints in the state space. So for instance, in the figure on the left, the Quadratic is trying to navigate around these obstacles such that, and the constraints are that it doesn't have to like collide with any of these obstacles. So there's this collision avoidance constraints, as well as the constraints of the dynamics of the quadrotor itself. And so the algorithm basically takes into consideration these two constraints, that's the dynamic constraints as well as the constraints for obstacle avoidance. And then it's also giving some cost function, which would probably be some, which could probably be minimizing the amount of talks that are or the amount of control command inputs that are sent to the quadrotors or something. Like you could come up with any kind of cost function, and then the robot would, well, basically not any kind, but then depending on the algorithm you're using, if you're using LQR, your cost function should be a quadratic cost function. But for most problems, for most difficult problems, cost functions end up being non-convex. And so there are ways to go around that. And so one example here is the quadrature, finding an optimal path around these obstacles. And on the figure to the right, it's basically a humanoid robot performing some really cool acrobatics using trajectory optimization. And so here, you realize that the constraints could probably be the dynamics of the humanoid itself, as well as maybe some other constraints. And then it's giving some goal states, where the goal state would specify the joints configurations and probably the center of mass, the target center of mass of the humanoid robots. And then the algorithm is basically supposed to perform a joint optimization, as well as considering all these constraints to come up with feasible sets of feasible sequence of command inputs or controls, as well as states, now to get the robot to reach those target points. And so that this shows that trajectory optimization is a very powerful idea, because by just formulating your problem as an optimization problem, you could basically use this algorithm to realize some really interesting and fascinating physical behaviors of robots, and that's I think that's really cool. So iterative LQR, that's ILQR, is basically a trajectory optimization algorithm. And an overview of ILQR or iterative LQR is as follows. So to solve a trajectory optimization with the main aim of iterative LQR is to solve trajectory optimization problems with non-convex cost functions and nonlinear dynamics. So you'd remember that when we talked about LQR earlier in the semester, we had this constraint that we had this condition that the cost function should be convex or quadratic, and the dynamics should be linear dynamics. But for most realistic problems, you realize that you could end up with a non-convex cost function and nonlinear dynamics. And one way of solving such problems for a longer sequence of a longer trajectory is basically using iterative LQR. So as the name implies, iterative LQR is basically just iteratively applying LQR for a sequence of time steps on some trajectory. And so how we basically perform, but then you realize that we have the condition in order to use LQR, the cost function should be quadratic or convex, and the dynamics should be linear. But then our problem has a non-convex cost function and non-linear dynamics. And so what we basically do is basically perform a second order Taylor expansion to approximate the non-convex cost function to make it convex. And then we'll also apply a first order Taylor expansion on the nonlinear dynamics to make it linear. So by performing these local approximations for each time step, you can then perform LQR for each of the time steps, and then perform this iteratively throughout the trajectory in order to come up with a feasible trajectory that's what we want you to do. So there's a brief primer on what LQR basically does. So with LQR, as I said earlier, we need to have the conditions for using LQR is that the cost function should be quadratic. So here the cost function is quadratic in terms of both the states X and the actions U. And Q and R are basically matrices that penalize the states and the actions or the controls based on some measure we are trying to optimize. And then the dynamics here is linear, with A being some state matrix and B being some control vector. And the aim of LQR is to get some control inputs that minimizes the cost function. And so to solve LQR, we talked about using the Riccati equation or Riccati recursion process to solve LQR. And that's there's a proof that there are some derivations that show that the Riccati recursion is basically the same as dynamic programming in some sense. And so we are now going to solve the LQR with dynamic programming. So with dynamic programming, we know that we already know the terminal cost for this cost function, or we know the cost at the end of the whole sequence of time. So if there are n sequences, we know the cost at the end of the whole sequence. That's like this quadratic. So given that we know this cost, we then want to find the cost for one time step. Yes, you're now stepping one time step from the final time. So if the total horizon is t, you're now going one time step, that's t minus 1. So at time step t minus 1, or n minus 1 here in this case, our cost function then becomes this expression where x now becomes x minus 1, x of n minus 1. And then, so that's the quadratic for the states and quadratic for the controls. And then this is the value function for the last time step, or the cost for the last time step. And then our goal is to come up with a sequence of, our goal is to come up with a control input U that minimizes this whole expression. You can then further factorize, or you can then further express this expression in terms of the dynamics using the A and B matrices. And so once we simplify that, we could end up with an expression that is basically in terms of A, B, x of n minus 1, and U, as well as the matrices Q and R. And so that results in this expression. And then because it's quadratic, and we know that in order to find an optimum for a quadratic function, you could basically just take the first derivative and equate it to 0. So that's what we do here. So we take the first derivative with respect to the controls because we want to find the minimum controls. So we take the first derivative with respect to U, and then we equate it to 0. And then we move the terms around, and we come up with, because we want to come up with an expression for U in terms of X. So when we move the expressions around, we come up with this expression on the second line. That's basically U multiplied, U is equal to, the U of n minus 1 is equal to some algebra of matrices R, B, Q, A, and N multiplied by the states X of n minus 1. So if we represent this whole thing, we could replace this whole thing by K. And so that's a control gain. So U is equal to K times X of n minus 1. So U of n minus 1 as the time step prior to the last time step, or the last but one time step. The control for the last but one time step is equal to some k gain. That's basically equal to all of that times the states, the last but one states. And so this is what we just did is basically equivalent to solving the Riccati equation to get the k. And so doing all of this gives us some control gain k, which we can then, which is basically a feedback control, because given this k, we could then supply any x, and that would give us the corresponding u needed to reach the target state. So this was L per R in a nutshell. And so we now move on to iterative L per R. So iterative L per R, as you can imagine, is basically doing this whole thing iteratively along some trajectory. And we basically have to perform the local Taylor approximations at each of the time steps, because as I said earlier, our cost function is non-convex and our dynamics is non-linear. So the iterative algorithm is can be basically summarized into these three lines. So while convergence is not reached, we then perform a backward pass to get some gains d and k. And these d and k are some vectors, which I'll go into details later on. So the first one is the backward pass to get the d and k, that's basically doing this for the whole time step. So we start from the time step t and go all the way to time step 1 to get the corresponding d and k's for each of the time steps. So once we have all these d's and k's, we then use them to perform a forward pass or forward rollout to get corresponding x and u trajectories. That's basically performing this expression, that's u is equal to k times x. Do this for the entire trajectory, that's the forward pass. And then we then get some x and u's. So once we get those x and u's, we check for convergence. If we haven't converged, we then repeat the whole thing again. We do the backward pass to get some new d's and k's, and then we calculate the corresponding x and u's using the forward pass, and then check for convergence. And we keep doing this over and over again until we converge. And once we converge, then the resulting x and u's are the optimal trajectories for the optimal trajectories we are trying to solve for.
Wait, I had a question. Wait, what is the convergence criteria here?
Yeah, I'll go into detail. I'll go into detail later.
Okay.
So this is more like a high-level overview of the algorithm. There's a lot of math coming, so I wanted to give you the high level. That way, once we start with the math, we don't get lost. But convergence is basically, we basically set up some value that the costs. So you can think of convergence like we have some goal targets, that's x goal, or some goal states, and we have some current states. So if the current states, or if the trajectory, the current state of the trajectory like reaches the goal states, then or the distance between, you could say some Euclidean distance between the end of the trajectory as well and the goal states. If it's like below some threshold, then it's converged or something. There are lots of ways of specifying convergence. In the code, they use a specific process of specifying convergence, and we'll go into detail in that later on. But this is just a high-level overview of LQR, iterative LQR. So let's go into more detail on what the backward pass basically entails. So with the backward pass, we initialize u and x to some u and x. So in the first run, u and x is probably going to be some vectors, or are going to be vectors or matrices of some random variables, or some initialization we could get from either or from some other process. So usually when people use trajectory optimization in a motion planning setting, they usually initialize the u and the x with the results from some sampling-based planner, and then that way it gives it a very good initialization. And so once you give it a very good initialization, we're just convergence in very few iterations. But if you give it some terrible initialization, it might or might not even reach convergence. So with backward pass, we first initialize u and x vectors, and then we initialize small p and big P to some random variables. We'll go into detail what these variables are, p's and the p's are. And then we then initialize some vectors, the d's and the k's. that's the gains. And then for each of the states x and u in the initialized u in it and x in it, we take the derivatives of the cost function to get some matrices A and B. And we use these A and B matrices to compute some gradients, some gradients. We'll go into more detail what these gradients are. Then we use these gradients to compute the D and the K. And then we use the D and K to further compute these P's. So initially it was initialized randomly, but then we then update the P's, and then we'll save the values we get for the D and the K that we solve for. And then we'll append all of them to these empty vectors, and then we'll return the D and the K. And so for the forward rollout, we then, based on the D and the K vectors we got from the backward pass, we'll then use the D and the K to solve for U. So for each of the time steps, we solve for U using this expression where it's basically almost the same as the expression for the L per R, but then it has this D factor as well. And then once we have the U, we then use the dynamics to get the x of k plus 1 for the next time step. And so that's the forward rollout. And now we're going to the algorithm in it. So we basically then perform the backward pass and the forward pass till some convergence is reached. And so how do we get all of these A, B, G, U, sorry, A, B, the G, small g, big G, D and K and P and big P. So that's what we're going to talk about in the next slides. There's going to be a lot of math. So anyway, so on a high level, the iterative LKR problem is to basically optimize some cost function or minimize some cost function over a sequence of states and a sequence of states X and a sequence of actions U or controls U, such that the system dynamics constraints are obeyed, as well as some constraints on the states and the constraints on the actions are obeyed. And so this cost function is often non-convex and non-convex cost function, and the dynamics is also non-linear. And so there's a cost function on the trajectory, as well as a cost function on the target trajectory. That's the last target, because we want to probably enforce the trajectory we're optimizing to actually reach the target trajectory we are expecting, or the target state we want. The target state is x of big N or x sub big N. And so that's usually how the cost functions are for trajectory optimization problems. And so this is a problem we're trying to solve with LKR, iterative LKR. So first, we can now express the cost to go. So the cost to go is basically telling us that what's the cost that's going to be incurred from our current states to reach the goal states. And so the cost to go for x plus delta x, that's when you're at x, when you take some states delta x, when you increment the states by some delta x, the cost to go is basically the current states, the current cost to go for the current state. That's the v sub n of x plus some p transpose delta x plus some half of some delta x transpose big P of delta x, where the small p is the nabla of, or the small p is the derivative with respect to x of the cost function, and the big P is the second derivative with respect to x of the cost function. And so in the algorithm I described earlier, in the pseudocode for the algorithm, this is what the small p and the big P represents. So the small p is the first derivative with respect to x of the cost function, and the big P is the second derivative with respect to x of the cost function. So usually the small p is a Jacobian matrix, or is basically a Jacobian, which is the first derivative matrix, and the big P is a Hessian because it's the second derivative matrix. So that's the cost to go. And there's also another function called the action value function, which basically states that if you have some states x and you take some action u, what's the resulting value you get from performing that action. And so action value function that's you get from when you had some state x, and so the action value function could basically be represented as the action value function of the current state plus some quadratic in terms of these G matrices. And we're going to talk about how you get the these G vectors and G matrices later on. But then simply put, these G's are basically the derivatives of the dynamics of the dynamics function. Well, we'll go into detail. We'll go more into detail later on. And so you can basically consider this as the action value function. And note that, so this is the relationship between the cost to go and the action value function. So the cost to go, or the value function, is basically equal to the value you get when the minimum, when the action that results in the minimum value is taken at some state x. So the cost to, so this is basically the relationship between these two functions, the cost to go and the value function. So given this expression, the next steps would be to replace this. What we basically want is that we want to get an expression for the u that minimizes this cost to go, this action value function. So that's all we want. And so in order to get this minimal u, in the next slide, we basically replace this s sub n of xu with the whole expression of x sub n. And that's what we do here. So once we replace this function, so we replace this s of n here with the whole s of n, the whole expanded expression of s of n, to get this long equation. So this is basically an expansion of this simple equation, so you don't get confused. So once we've gotten this, we actually want the delta u that minimizes this whole thing. And because it's a quadratic, and you can tell it's a quadratic because of the x transpose times some matrix times x. So usually when you see these x transpose times some matrix times the x, or u transpose times some matrix times the x, you should know that this is a quadratic expression. So because this is a quadratic expression, we know from basic calculus that in order to get an optima for a quadratic function, you can basically just take the first derivative and equate to 0. And so because we want the optimal u, or that's the minimum u, we basically take the first derivative of this expression and equate it to 0 with respect to u, because we want u. So we take the partial derivative with respect to u and equate it to 0. And we end up with this expression. And so once we have this expression, we can then make u the subject of this whole equation. And so delta u now becomes this simple equation in terms of big G's and small g's and delta x. And so this is the final expression for u we get. And then we make everything simpler by replacing this expression of big G of which is basically a second derivative of I'm not talking about second derivatives now, it's going to be confusing. So it basically represents this whole big G of inverse big G times small g all sub u. Replace that with the variable d of n minus 1. And then we then replace this inverse of big G sub uu times big G sub ux. Replace all of that with this variable k. And so just like in LQR, we basically just wanted to replace the whole thing with some simple variable. That way we can manage things well. And so just like in LQR, we now have an expression for delta u in terms of delta x. So delta u here is just like minus d of previous time step minus k of the previous time step times delta x. So we now have this d and the k. And so if you remember in the algorithm, the pseudocode, this is how we compute the d and the k. This is how we compute the d and the k. So these are the d's and the k's we need in the pseudocode algorithm. So that's how we compute the d and the k. So you've now been able to figure out the p's as well as the d's, the small p, big P, as well as the small d and big K. So the next step would be to figure out where to get the g's. And so the small p and big big P could then be, so once we have this expression for U, for delta U, we can then put this expression back into the value function or the cost to go function to, we can then put this expression for U in the cost to go function. And looking at this factorization of the cost to go function, we factorize it in terms of small p and big P. And so once we replace delta U, once we replace the delta U's in that function with the one we've got in here, we then end up with a very long equation, which I didn't write. And once you basically group them in terms of big P and small p, you end up with these equations for big P and small p. So big P would be equal to this giant equation, which is made up of big G's and big K's and small G's and big K's. And so based on this D and the K we've gotten from the previous step, we can then use that to calculate the big P's and small p. And then once we have the big P and small p, we can then, the small g and big G matrices, they are obtained from the first and second derivatives of the action value function. That's the S. So once you take the first and second derivatives of action value function, we then get the G's. So the small g of x is basically the first derivative of the cost function plus, it's basically the first derivative of that function, of the action value function with respect to x. And then small g of u, or small g sub u, is the first derivative of the action value function with respect to u. And big G of xx is the second derivative. So it's basically taking the first derivative, taking the derivative with respect to x twice. So it's basically a second derivative, all with respect to x, of the action value function. Big G of u is basically the second derivative both with respect to x, first and second derivative with respect to x. And then big G of x, small x u, is basically the first derivative with respect to x, the second derivative with respect to u. And then this is the first derivative with respect to u, second derivative with respect to x. So all of these are Hessian matrices. That result from taking the second derivatives. And the G's would probably just be Jacobians or scalars based on the dimensionality of the state. So we now have all the variables we needed to perform the LQR algorithm, to perform the backward pass. So we figure out a way to get the G's as well as the D's and the K's and the P's. But I think A and B, I think I mentioned it. So A is the first derivative of the dynamics with respect to x, and B is the first derivative of the dynamics with respect to u. So we now have all the variables we need, and so basically can implement the LQR algorithm now. So as a summary, the iterative LQR algorithm works like this. So we perform the backward pass to get all those variables simply to get the D and the K. So the main goal is to get the D and the K. Once we get D and the K, we then use the D and the K to get the U, and then we use the U with the dynamics to get the X. And we perform this over and over and over until it converges. And as a summary, this is the backward pass algorithm. We get all the variables, the values of these variables. And the forward rollout, we basically use the D's and the K's we calculated from the backward pass to get the U, and then we then use the U as well as the previous states with the dynamics to get the next states. And this is performed till convergence. And usually people don't just perform the forward rollouts as it is, because it could happen that because this is somewhat of a Newton method, the steps might be too big, and so it might reduce the chances of convergence. And so they usually use something called a line search, which I'll show in the code, to basically make sure that the step sizes are small enough to reach convergence. So it basically just minimizes the step size, but that's just an addition. So this is basically the forward rollout algorithm. And so that's it for the LQR algorithmic explanation and how to derive all those variables. And now we are now going to look at the code for these, and it's implemented in Julia. So this is a nice ID. It's called Juno. It's a nice ID for using Julia because it gives you access to almost everything. It's kind of like MATLAB, but it's built off of Atom, the Atom IDE. So this is like a Julia plugin for that. So it's pretty cool. So this code is basically using LQR to perform to control double pendulum, and the goal is to basically get a double pendulum to be at 90 degrees upwards. So the initial state is the double pendulum will be facing downwards at negative 90 degrees, and the goal is to get it to be facing upwards pointing upwards at 90 degrees. So that's the initial state and the goal state. And yeah, so I'm gonna go to the code. So we import all the libraries we need. We need a linear algebra and some plotting libraries, as well as the forward diff. This is for performing automatic differentiation of functions. It's pretty cool for getting the derivatives and the Hessians I talked about in the algorithm. And RobotZoo sorry, RobotZoo basically gives us access to the dynamics of the double pendulum, or the acrobats. I'll call it double pendulum. And so we describe here, this function describes the RK4 integrator. So basically it describes the dynamics. So RK4 is just a way of like performing dynamics by integrating the dynamics equation multiple times. So it's you can think of it as an interpolation of the dynamics. But that's just an aside. We didn't go more detail into it. And so we then specify the parameters. So our state is going to have a dimension of 4. So the state is 4-dimensional. So the state is basically made up of, so the I think there's a, yeah, so this is the double pendulum, and it has 2 actuators, or 2 motors. So the state is made up of the angular reading or the angular displacement of each of the motors. So first dimension is the angular displacement of this motor. The second dimension is the angular velocity of that motor. The third dimension is the angular displacement of this motor. And the fourth dimension is the angular velocity of that motor. So that's why the nx is equal to 4. And the control x is, because the control x is 1. So in this case, we are only controlling this second motor. We are not controlling this one. So it's a canonical under-actuated system. And the total time horizon you're going to be looking at is 5 seconds. And so this basically specifies how long the whole trajectory is going to be. So we could probably increase it to 15 seconds, and that would basically determine the kind of controls we have. It's not going to be as aggressive as it would be if we give the small amount of time. And we then initialize all the time steps into some. We then get the total time, or the total horizon, split it into time steps. So each time step is 0.05 seconds, as specified here. And then we get an array of that. And then we specify the Q and the R matrices. So when we did LQR, we said that the Q matrix is for penalizing the states, and the R matrix is for penalizing actions in the cost function. And so we could come up with, we could basically design our own matrix. So usually in practice, these Q and R matrices are designed by the user. So the user specifies how much are you going to penalize the states versus the actions. And the Qn is basically the final cost, or the cost for the final state. And because we really wanted to reach the targets, we create a very huge matrix. So there's like 10,000. So there's an identity matrix. I is basically an identity matrix of the same dimension as the states, but then it has like 10,000 across the diagonals. That way it has a very heavy penalty to basically make sure that the optimization reaches the final targets. And so these are the cost functions. So this is the stage cost. So the stage cost is the small L that's like along the trajectory. And the terminal cost is the final cost that's supposed to ensure that the robot reaches its goal. So that's why we use the QN. That has a big penalty. And so the cost function basically concatenates these 2 functions. So if you've not yet reached the final cost, or the final state, we then use the stage cost. But then once we reach the final state, we use the terminal cost, and we append all of that to some G. So this cost will basically return the cost function G I described earlier. And this system is nonlinear because it's a double pendulum. And so if you've used a double, if you've had access to a double pendulum, like in the real world, you realize that double pendulum is very chaotic. It like swings all around. And so it's highly nonlinear. And so we then specify the initial guess. So the initial guess is, or the initial state of the pendulum is that it's going to be pointing downwards. So this whole thing is going to be pointing downwards. And the goal state is that we should control it. We should add controls to this mode such that it will make it point upwards. And then we initialize the trajectories to some random numbers. And so in practice, if you wanted to use trajectory optimization on some motion planning problem, you'd probably, what most people do is they use sampling-based planner to plan some initial states. And then they then use those initial states as like initialization for the trajectory optimization. But here, because it's a simple problem, we don't really need that. So we then initialize it to some random numbers, basically. And so this is the initial rollout to basically get giving the random numbers for the controls. We then use the random numbers to get the dynamics. We then pass them into the dynamics equation. That's the dynamics function. That's the F. So in our case, this is the F to get some corresponding states, and we save the whole states into the vector x traj, u traj, and then we then compute the costs of this x traj, u traj. And so this is the whole iterative LQR algorithm. It's also called the DDP. That's a deterministic dynamic programming, which was like, so DDP was proposed sometime in the 80s, I think, and then Imo Todorov, this group at University of Washington, proposed the LQR, iterative LQR, I think 2004. That's the paper I linked. But they're basically the same algorithm, but the iterative LQR omits some Hessian value that's like not that necessary. But it's basically the same as the DDP. So this is where we go into the algorithm I described previously. So we initialize the small p, the big P, the small d, the big K, and delta J. So delta J is the change in the cost function. And we initialize them to some arbitrary numbers, to zeros, basically, zero vectors and zero scalars. And then small g initialized to zeros, zero vectors. Small g of x is that's basically the first derivative of the action value function with respect to x. It's just zeros, a zero vector of 4 values because n of x is equal to 4. And because u has a dimension of 1, control has a dimension of 1, it's just 0.0. And the gxs is the Hessian, that's the second derivative of xx, as I described earlier, and the others, they're all initialized to zeros. And then, so this is the whole algorithm. So this is the while not converged. So here our convergence signal is if the absolute value of the d values we get is still greater than 0.0004, 0.0001. And you could always specify your signal for convergence. It's just not absolute. Some people also use the change in the cost function as a signal for convergence. So if the cost function from the previous iteration and the current iteration, if the difference is like less than some value, then some threshold, then we are converged. But then here they're using this d. I don't really know why they're using the maximum of it. I think because the d is probably supposed to tell us how much it's converged or something. I'm not sure. But this you could basically replace this with some other convergence, some other reasonable convergence signal, and the algorithm is still going to work. And so we've initialized all the variables we need to zeros and whatever, and we initialize. So we first initialize the p's to zeros and initialize the d's. I think this is not really needed because we've already done it here. That's just a repetition. And then we first solve for the, we first basically initialize the small p and the big P to some values which is equal to the penalty. Oh, sorry. So the small p for the final time step, that's the time step at the end of the trajectory. We initialize it to the penalty for reaching the target trajectory times the difference between the states, between the last trajectory in the trajectory estimation and the actual goal we are trying to reach. So they're basically finding the derivative. So that's basically, that expression is basically the derivative of this function, this final cost function. Because p is the derivative of the cost function. And so that's it here. So for small p, and the big P is the second derivative of the small p. So when you take the second derivative of this equation, you're going to get just qn. So that's it for the p's. And then we then perform the backward pass. So the backward pass is this. So q here is basically the convenience variable that is basically the derivative of the value function with respect to x, and small r is the derivative with respect to u. We then calculate the a and b. So a and b is the first derivative of the dynamics function with respect to x. And so we use the forward diff Jacobian because so forward diff is basically an automatic differentiation or auto-diff function feature. So it basically takes the derivative of this f, that's the dynamics function. And we perform the same thing here. So this is a Jacobian because the state is 4-dimensional. So the matrix is going to be 4x4. So we need a Jacobian for that. But then because the u is just a single dimensional, 1-dimensional, you then call the derivative function instead. And then so we get the matrices A and B. So B is probably going to be a scalar. So you get A and B. So once you get A and B, we then calculate based on the equations in the slides. We calculate small g of x and small g of u. And these are the equations in the slides. And then we calculate the g of xx, g uu, g xu, g ux. And then we use these values to calculate the small d and then small k at that time step k. And then we then calculate the small p and the big P using the g values we put in based on the pseudocode I described. And then we increment the delta j. We don't really use it here, but if you wanted to keep track of how much the cost function is changing, you could probably use this. And so this is basically what the backward pass does. So it performs this backward pass once, and then what we really need from this backward pass is the d and the k vectors. So once you have the d and the k vectors, you're going to use them for the forward rollout. So the forward rollout. So with the forward rollout, you basically perform the forward rollout once without line search. So this is the algorithm in the slides. So we get a u, and to get a u, we use the d and some alpha factor, which is initially 1. So we use that equation in the slides to get it. So we use the u here. So we use the d and the k, and the big K we got from the backward pass to get this u of k. And then given this u of k, we then use the dynamics function to get we put the u of k we solved for, as well as the current state x of k to get the next state x of k plus 1. And we perform this for the whole trajectory. So this is the forward rollout. And then in order to make sure that the step sizes are small enough, we use something called the line search. So this is called the immediate line search. So this is basically just for convenience. It's not really part of the algorithm. It's just like a thing we do to make things much nicer. So so this is immediate line search. So you can probably read about it more. It basically tries to reduce the time steps in order to ensure convergence. And so we do this, and after doing that, we then initialize the x charge to the u and the x we've gotten so far, and then u charge to the u and the x we've gotten so far. And then we use this X and U charge to initialize the X and the U's on the next time step. Yeah, we use those X charge and U charge to basically run the backward pass on the next iteration, and keep doing this until we get some trajectory, X trajectory and U trajectories that converge. And so once it converges, we then perform the trajectory optimization. So the next thing we need to do is just visualize the trajectory we performed so far. And so I'm going to run this whole script. So I'm going to run this whole script. Let me save it. I'm going to run the whole script, and yeah, it's a bit buggy, but it usually works the third time, fourth time. I don't know why it's not working. Yeah, it's not displaying for some reason. Display. Oops. I probably change something. I should have changed. Oops, no. All right, if it doesn't work, I'll restart the Julia REPL, and that might work. So the problem is that it's saved all my system variables here, and so it's probably using these values, and that's probably causing the problems in plotting. All right, let me quit the REPL and restart it. This is the last part of the reading group. I plan to do another demo of an actual robot arm that's reaching for something, but I had internet issues in my new apartment and I couldn't get things done. I couldn't get it done, so maybe I'll work on that and probably send a link to Slack or something. And so because Julia is a just-in-time compiler, when you first run it, it compiles all the libraries. And then on the second run, it's going to be very fast. So the first time you run it, it's probably going to be very slow. Oh, it's still compiling. Yeah, but that's mostly it. I want to show this animation. I will be done. The nice thing about this IDE is that you can have your visualization alongside your editor, file manager, and then Git all in one on one system. And so when you're doing development, it's very convenient. So this visualizer is a mesh cut visualizer, and most of the Julia robotics people use this mesh cut visualizer because it's very flexible.
I think you can do something similar in VS Code.
Oh yeah, VS Code. Yeah, you're right. Wait, does VS Code have a Julia plugin? I think they do. They do, right?
Yeah.
Nice. Still compiling. Usually when people say Julia is much faster than Python, they usually don't mention this, the time it takes to actually compile the libraries, like the initial compilation of the libraries. They usually don't factor that into the comparison. So even though after the first run, subsequent run is going to be like really fast, just like C++, the first run is always very slow. And so I don't know, they should be more open about that. You realize that they never actually mention it, that because it's just in time compilation, the first run is going to be very slow. They never say anything about that. So it's a bit deceitful. But I guess even with C++, when you're compiling, it takes some time, right? So yeah, I guess that.
I'm curious why it takes like, oh, I guess it's ready now. So
Yeah, it's
or almost ready. I don't know.
oh yeah. Oops, no, it didn't show. For some reason, it's not showing. Let me run it again. I mean, it's running in a. Run it again. Looks like it's showing in a web browser. I don't want it to show in a web browser. Oops. Let's do it again. Yeah.
Oh, why did it take so many tries?
I think there's a bug. It's a bug with either my code, either it's a bug with the code or it's a bug with the mesh card itself.
Well, it looks good now.
Yeah, now it's working. So I could replay it. Nice thing about this mesh card is that you can basically replay the whole thing. It saves the whole. So this is the iterative optimization in action. It plans the whole sequence of like states to reach the final state. And because there's a heavy penalty to reach the final goal, it actually works. So I could probably change some parameters in the code and we'd see how it works. So I limited the runtime to 5 seconds in the code. That's why it ends at 5 seconds. So I could probably change the whole runtime to 10 seconds and it would be much slower. There'll be more states. So 10 seconds now. Hopefully it doesn't break the code. It's frozen. What the heck? Ah, nice. It's back. Come on, this thing again. It's not showing. So it's running, but the visualization. I bet if I did it in a web browser, it would probably show, but I don't know. I don't know why. Take a couple of tries first. You just keep running it. I don't want to do it in a web browser. It takes away the magic.
Magic.
I like that the display is in the editor itself. I'm just gonna do it in a web browser. So come on, one more time.
What is the phrase? Madness is assuming it's trying the same thing 30 times and expecting a different outcome.
It worked the last time, right?
It did though, yeah.
All right, let's look at it in the web browser. So wait, it's not showing here too.
Yeah, it's probably a bug. Probably a bug.
Nah, but it's oh yeah, it's probably a bug.
Oh, I guess we saw the thing, so it's okay.
Yeah, but now because I increase the time step, it's going to be much more. It's going to be much slower, and it's going to do some other acrobatics before it reaches the final. And I just wanted to, but I could send you the code. I could put the code on GitHub, and you could probably play with the parameters.
Yeah, fair enough.
I was going to say, as long as you get it working once, you record the video and then you don't have to worry about it. I have several projects that I have one video from the one time that worked.
Oh my.
And I won't tell you which ones.
Yeah. So that's it. I wanted to have another demo, but my internet was terrible, so I couldn't work on that. But
I think the double pendulum is a really great example because it's like every person, if you've ever done a controls project, you've done something with a pendulum. Yeah. I think it's really easy to sort of look at how it's converging, and you can see something. You can see that like you can tell it's going to a local solution first before it finds the global.
Yeah.
Which is interesting to see, but it does still find the global where others might get stuck.
True. If only this visualization could work correctly. Oh, it's probably because of something I'm doing in the code. Let me take out this line. So this line is supposed to cause it to render in the IDE. So now we're just gonna go web browser through it. Let me stop compiling. Yeah, it takes so long to compile. But yeah, that's it. So if you want to stay around and watch the whole thing awake, then yeah, we can still keep at it.
All right. I think I'm gonna head out now, but thanks for producing like this great demo and giving the presentation.
Yeah,
Sure.
same here.
Good luck getting the visualization code working.
Yeah. I'm pretty sure it's gonna work right after you log off.
Well, that's how it always goes.
Yeah.
All right.
See you Bye, guys.
All right. See ya. Thanks.